OpenFoam is a powerful software to do the safety simulation. We need to provide the description about the input geometry and initial status of the flow field. The associated solvers in OpenFoam can help us to show how safety simulation data change with time. The lead-driven example is a classical tutorial of the OpenFoam. The geometry is just a simple box, and there is an initial speed at one edge of the box. Then we can use OpenFoam to simulate the change of the fluid in the box. In this video, we will discuss how to generate the simulation data of the lead-driven example based on default parameters, and then we will show how to use Paraview to do the post-processing for the generated data. Furthermore, we will explore how to change parameters of the simulation to create different simulation results as needed. Okay, let's see how to install the OpenFoam, build it, and run the simple example. This document provides detailed information about how to install and build the OpenFoam. We do not go through details here, and if I follow those steps one by one, you can install the OpenFoam successfully. In our example here, I could show you my current repo. Here, I download this TGZ file and install the OpenFoam successfully here. And after build and install this, if we want to execute some like simple test, the first thing we should do is execute this source OpenFoam etc-rc. After doing this, we can load the necessary binary files built by OpenFoam, such as this OpenoFoam solver. And the next step is to start to execute some simple simulation. Let's look at the tutorial. First is that we copy the tutorial from the our OpenFoam folder into our working directory. The example we targeted in is this one, OpenoFoam cavity, and my working directory is this one, OpenFoam. It is empty now. We copy it here. Get this, and there are several tests. This is one that we focus on. You can see that each case have a similar directory hierarchy, their own constant and system. We do not go through details here, but anyway, you could see that those are some configurations files for initial status and how to run the simulation, like timestamp, start time, end time, and particular parameters. But anyway, we will discuss those details later. Let's first see how to use those default parameters to run examples. Let's jump into this cavity. First thing is to run this block mesh. After doing this, the OpenFoam can help us to generate the mesh file used for simulation based on the descriptions in those files. And next step is to execute the particular solver based on the configurations here. The solver we use is called OpenoFoam. See, it's easy. Let's do it again. We execute OpenoFoam and got a bunch of files here. Every directory includes the parameters of the simulation. In the simulation, you can see there are particular descriptions of that data and particular values in that data. That's an easy thing to do. Just execute block mesh and then OpenoFoam. Get what you want. Okay, after getting those data, we want to visualize it. For example, we can use Paraview to visualize those data. If we happen to install the Paraview in our server, we can always execute this Paraview to trigger the Paraview and run that. But in this server, I didn't install it. What I usually do here is to just copy the data back to my local machine, and then to execute the Paraview in my local machine. So this is on my virtual server, and I copy this data into my local machine and do it. Yeah, we got those results. Let's look at those results in the local machine. Yeah, you can see the results here. But how to load those data into Paraview? Actually, it's a really simple thing, and the Paraview is a dummy file to recognize the data format. You know that Paraview can support all kinds of data formats such as VTK, those kind of things. In this example, we just need to create a dummy file. Any name can work here. Let's say we just call it test.form. This FOAM is important, and the Paraview uses this dummy file to understand, to know that what kind of data parser they should use. By doing this, and let's open the Paraview here and load that data to see how it works. It's in download, test, cavitate. If we just double click this test.form and hit apply, yeah, we can get these results here. This is our box, and there is a initial velocity at this edge, and all kinds of parameters. U and V, we might more interested in this value, and we only have 10 time steps here. It doesn't change a lot, but anyway, we just want to show you how it works to visualize the data in OpenFoam, and then you can use all kinds of filters here. And for the next step, we will try to understand how to change the particular configurations and parameters and to get the results we want. For example, we want to say how that fluid move around time, like it change around this way. For this case, if we click the stream tracer like this, you can see it changes a little bit, but not much, and which might really helpful. If we load the previous data set, and this one, if we load this old data, yeah, you can say it is quite complicated, and with the change of the time, we can say the flow fluid change in different patterns, and get those interesting results. We do not dive into details here, and I just want to show you how to use different filters to get the particular effects we want. The particle tracer is really a useful one if we don't show those things and only show the particle tracer. We can see the particles that the Paraview can help us to trace the particles. The initial particles are located on this line. And another interesting filter is this glyph. We use this glyph to add a particular points here. Actually, it's just a sphere. And next thing is a temporary particle to path. If we don't show this, and say here there is a glyph, and every glyph can lead there is a particular line here, and you can set different parameters to get more interesting results. And anyway, let's look at how to generate the data sets used for this visualization. Okay, let's go through specific parameters defined in OpenFoam. And there are three typical folders: zero-zone, constant, and system. For this zero-zone folder, it defines parameters we need to simulate by the simulation. In this example, we have two parameters, p and u. Let's go through p firstly. The form file describes the object, class, and format for this parameter. This thing is interesting. It defines the specific unit for this parameter or field. Let's say you can get a particular definition of a unit here. For this example, if the second digit is 2, it means it is a meter square and per second. So in this example, if it is a 1 and -1, it means a meter per second. So this is the unit for the field. And the remaining part describes the boundary conditions. We can see that there are different types. We do not go through details in this video, but you can get some ideas here. In this driven lead example, we have a moving wall at the top of the box, and it has some initial value which defines a particular initial speed. And for this parameter, there is no definition. No initial value. This file in constant directory called transport properties, which defines particular parameters for a model, describing the model. In this example, we only have one parameter called nu, which is a viscosity in the fluid. You can get more ideas here, like the OpenFoam simulations that includes flow without energy heat requires this particular property, and we define it as nu. And if we change this parameter, we can see different effects of the simulation data. For example, two figures here show how we change the different value for this parameter and get different results for the same time step. And other parameters are same, but we only change this parameter. You can see that there are different circles in different simulation results. Multitude parameters are defined in this system folder. Let's look at the block mesh directory first. This parameter is really interesting scale. At the initial state, this one is 0.1, and when I generate the mesh, I found that I generated the simulated data. The data does not move, and actually it can move if we change it into 1. And what are difference here if I set it as a 0.1 and execute the block mesh here? We can see the generated mesh file, like every point. It seems that every point is multiplied by 0.5. You can see here. However, in our parameter here about the p and u, actually the unit is 1 meter per second. So we actually only simulated a particular small domain by this way if we set as 0.1. So if we set it as 1 and regenerated the block mesh again, we can see that the upper bound change. The upper bound will be 1 in this case, so it simulates the domain from 0 to 1. which can generate the particular results we want. And the other parts describe the geometry, which I think it is really common with other different softwares, vertices, blocks, and edges, and the boundary here. Control directory show more common parameters such as start time and time of simulation, data of the particular simulated model, and the write interval and time decisions, etc. We do not go through every details here, and you can find different particular documents online to get more ideas. And for subsequent files, there are more details. I think they are related to control the model, details of the model, and some particular parameters. We will look at those configuration files in future.